Alright, well, I'm going to put an X on this one. Well, I guess the condition for me to like check off these streams is that I put 5 minutes of work in, and I have 30 minutes left in the block. We'll say 7:30 to, we'll do an hour here. The check mark is just for me to indicate that I got on stream and I did at least 5 minutes of work. We can just say wasted time this morning. Wasted time. Brown. I think I'll eat breakfast. We'll see. We'll see how much I want to wait for that. We'll put that there for now. Okay. So today all we have to do is get through all of our lectures, our remaining lectures. So we started on network programming. I'm going to 2x speed all of these because
and similarly, I as a client might have connections to dozens of hosts going at any given time. I'm choosing the web, I'm doing all that different stuff. And that's all differentiated at the client end. That there's different ports associated with your different programs that are running. And so a port then is an integer that identifies which particular endpoint is being communicated with at either the client side or the server side. And typically at the client side, these are assigned dynamically. And they're referred to as ephemeral ports, meaning they only are assigned for the limited duration that you have a connection with that, that you're maintaining that connection. And then there has to be some way, if I'm going to contact, and I want to know, the DNS will tell me what the IP address is of, say, google.com, but I have to know that am I communicating with its web service, which is port 80, or HTTPS, a secure socket is a different port number. So which service I'm asking for. And there's a standard list, what are called well-known ports, that are that I can contact at the server end to get the particular service I'm looking for. And those are assigned. There's a big list of port assignments. And so, again, that's part of the sort of whole set of internet standards is the identifiers for the different ports, what services those are, and how those particular protocols work. So when I have a connection then, as I mentioned, think of it as a connection then as a link between two machines based on some known port, typically at the server end, and a dynamically assigned or ephemeral port assigned at the client end. And I can refer to then that connection then is identified by the combination of the hosts at the two ends and the ports that they're using. And in general, then, it's the job of the kernel to differentiate the different connections that are coming into a machine and figure out which software, which process to wake up when when some data arrives from another machine, and which actual program running on that machine will make use of that data. And that's done by associating for each of the ports a particular process executing program that's going to handle those particular requests. And it's totally possible for a client to be interacting with a single server over different ports, but those are considered to be different connections, and so they don't really interfere with each other. So that's what I mentioned is this is what we refer to as sockets programming, or the sockets interface. And it was developed sort of as the internet was evolving in the late 70s and early 80s. So socket then, as I said, is sort of logically one of the two ends of a connection. And from an application point of view, you'll see it as a file descriptor, just the low-level file stuff that you've already seen that you can do reading and writing from. And so that's the sort of mental model that is provided by the socket interface. But it's a very different, the actual implementation of network. When you write to a socket, it's firing up all kinds of network stuff, whereas you write to a disk, it's operating a disk controller. So at the hardware level and even at the lower levels of software, they're very different pieces. But you as an application programmer see some commonality there. OK, so let's jump right into the API. And again, this is a place where you'll wish you were programming in a language that had type hierarchy, but you aren't. You're programming in C. So there's a zillion structs that you kind of have to get familiar with, but one's called a sockadder. And basically, it's just a 16 bytes worth of stuff, where the only thing that's special here is that the leading 2 bytes designate what type of socket this is. In particular, it would be different whether it's a TCP socket, an IPv6 socket, a UDP socket, and all those will have different numbers, a different constant in there that tells you which type of socket it is. And then at the high level, the sockets, a lot of the programs don't need to know, which type of connection this is. They can just deal with, they basically call other software to deal with that. So that's why it's referred to as being family specific. And then the socket stuff isn't even necessarily referred to the internet, the capital I internet. And so there's a more specific one called a sockadder_in that is used for IPv4 sockets. Not IPv6. And so in particular, it fills in fields. One is called the port, which, as I mentioned, is 16 bits, and then the IP address, the 4-byte IP address, both of which are in, even if you're running the software on a x86 machine, these should be in big endian order. And you'll see that this is what I mean, that this is sort of a C's version of subtyping, if you know something like C++ or Java or you know, a language with type inheritance. That you can think of it as a sock adder in as sort of a subclass of a sock adder. Right? It has more information, it's compatible with, but has more information than a sock adder. And then there's another type for IPv6 has a different kind of struct that they fill in for its information. And then they pad it out with 8 bytes of zeros, just because this particular protocol doesn't require the full 16 bytes. Okay, so this is sort of what it looks like to operate a full-blown client-server system from a programmer's perspective. And we're going to, for the rest of today and all of Thursday, go through all these steps. And you, as a programmer, are actually going to have to understand each of these steps, what they do, what they mean, and how to use them. The good news is there's some pretty standard patterns here, and so you can often grab some existing code, say out of the book, to use that will make this not as painful as it might look. So, but the overall idea of this picture then is, sorry, I can't get used to the fact my remote doesn't work. On the right-hand side refers to the steps that the server has to go through, and the left-hand side is what the client does. So the upper right is what it takes to set up a server that is then a program that's running there, ready to receive connections from a client and perform various services. And so obviously, before the client can do anything, the server has to exist. So that has to be the first step in setting things up. And then we'll fire up a client that will make use of this service. And then there'll be what's referred to as a session, meaning a kind of back and forth communication between the client and server doing whatever they're going to do. This is not specific to any particular application. And like I said, it will involve, you'll see Rio underscore. Remember, those were reliable I/O functions that we talked about as part of the Unix I/O. So it's a way to read and write and handle some of the quirks of low-level I/O. But basically, this is sending and receiving messages over the internet. And then once that's done, typically then the client will close its connection, sort of the equivalent of hanging up its phone, and say, OK, I'm done. And then sometime later, or maybe never, depending on what kind of web service this is, if the server wants to shut down, it has its own collection of calls that it makes to stop that service. So anyways, just to kind of give you the landscape of what this picture means. So we're going to sort of jump into the middle, the top level, and we'll focus. Actually, which will we focus on? Well, we'll talk to some level in parallel, because there's a lot of commonality, as you can see, between what goes on with the server and what goes on with the client. And so actually, the top level call, this one called getAdderInfo, is the way that it sort of initiates things. It actually does the lookup to map from a domain name to an IP address. So we'll cover that later. So the first step on either side then in creating a connection is a call to a function called socket. And the reason I wanted a blackboard was to help you keep track of this. So the first call doesn't do much, and that's why the function call is socket. But it only happens within the application. It doesn't make use of any part of the operating system. Doesn't send anything over the network. Basically say, hey, I want to create a socket. And
Wait a minute. I don't think that's quite true. Man to socket. Man syscalls socket. Yeah. It's definitely a call into the kernel. You wouldn't be able to get a file descriptor out if you didn't talk to the kernel. He's saying it's not going into
the operating system, doesn't send anything.
Here.
It only happens within the application. It doesn't make use of any part of the operating system.
Doesn't make any use of any part of the operating system. Well, that's just demonstrably false because you're getting a file descriptor out. The kernel has to know about the file descriptor. And you're making a syscall socket. Socket is a syscall. So that's making use of part of the operating system. I don't know. There's a lot in this course that I've just kind of realized that they get the broad high level overview really great for undergrads, but on specific technical details sometimes they show incredible insight. And then sometimes they just kind of gloss over things that are just factually incorrect. Especially in the worked examples, the practice problems that I've done. There's just so many mistakes in that it makes me question their competency. But I know from the lectures and just from reading the book that they're quite competent people. It's just they make a lot of mistakes on some of the technical stuff. And even in the lectures, some of the students have called them out on things. So this is one thing that I just don't understand what he's saying. It doesn't make any use of the operating system. What is he trying to communicate there? Because it's clearly making use of part of the operating system. Let's back up a little bit, see maybe we can understand better from what he's saying in context. Protocol specific best practice is to use getAdderInfo to generate the parameters automatically so the code is protocol independent. Okay.
The first call is a so the first call is a doesn't do much, and that's why the function call is socket. But the
That's right, it doesn't do much.
it only happens within the application. It doesn't make use of any part of the operating system. Doesn't send anything over the network. And the idea is to basically say, hey, I want to create a socket.
Doesn't use.
And it's given 3 arguments.
I think what he's trying to emphasize here is that it doesn't do much, which is true, and that it doesn't send data over the network. But it does make use of facilities in the operating system.
The first of which is AF_INET. All these uppercase names are constants that are built in. They're included in the various .h files that you include in writing this code. And AF_INET just means it's a IPv4, so 32-bit addresses. And then the second parameter is, says you want a sock stream, and that refers to a TCP connection. It's referred to as a stream connection because, like I said, you get to send as many bytes as you like, a stream of bytes in either direction. And then 0 protocol. Well, I guess it must not be very interesting because I set it to 0. So we don't need to do anything in this particular case. There are man pages on this, by the way, which if you just tried to learn all sockets programming by reading man pages, you'd go crazy. But once you kind of have the idea, it's pretty useful. And then the next part, you'll see we're looking only now on the server side. It's called bind. And
pause there makes me think that and the fact that he didn't know what the protocol argument to the socket syscall is for, makes you think that he's kind of like winging this lecture to a certain degree. I mean, so bind, let's just go through everything. Get adder info, so you're giving some type of address information, a host name, a service name, a IP address, and a port, and you want to resolve that into like, is it like what is it the family of the address? First, let's resolve the names to addresses. So getting from strings into numeric actual addresses. So this will be resolving the service name to a port number, resolving the host name to either an IPv4 or an IPv6 address, and then indicating what the family is. So that's what getAdderInfo does. And I'll use DNS. It'll use your Etsy host file. I think there's an Etsy services file it uses to resolve the service, but that's its responsibility, is turning the human readable strings into machine readable actual addresses. And it actually gives you back a collection, because DNS can respond with like multiple IPs of different families to a given host name, because you can get quad A's and you can get A's. So yeah, there's a number of different addresses, numerical addresses, that are returned from getAdderInfo. So once you have that information, you can create your socket, and like you said, it doesn't do much. All it does is give you back a file descriptor. And once you have that, you call bind, which tells the kernel, hey, this is the port that I'm interested in listening on eventually. So that kind of like tells the kernel, hey, I want this port. If the port's already bound to another process, then you can't bind to it. And you have to handle the error case there. So assuming your bind succeeds, now you have a socket that's bound to a port, and then you call listen to tell the kernel, hey, I want you to allocate a buffer of pending connections. So start accepting connections and land them in this buffer that you're going to maintain, and I'll give you the size of that buffer. And then I'll call accept on this socket, and when I accept, you'll give me the next connection in that buffer. And then I'll do IO on that connection file descriptor, and at the end I'll close that connection file descriptor. Yeah, so that's like the basic server workflow. The client workflow is a lot simpler. Does the same getAdderInfo to resolve a numerical address, and then calls socket, same type of socket call, and then it just calls connect instead of this bind, listen, accept. The connect just gives the tells the kernel, hey, initiate a SYN-ACK TCP handshake. Assuming it's TCP, could be any number of protocols, or even just raw IP, because the socket API is pretty flexible. I think socket itself takes in your if we go back to, actually I'll just pull up the man page here, man2 socket. So you give it the domain, which is IPv4, IPv6. Oh no, sorry, domain is INET or Unix domain. That's synonym for Unix domain. So yeah, iNet is IPv4 and iNet6 is IPv6. So these are the three ones that I'm familiar with: Unix, iNet, and iNet6. The rest of these I have no idea. And then type would be whether it's datagram or stream or raw. These are the three that I'm familiar with. So that's all done in the socket call, which makes sense. All right, let's continue on with the lecture here.
What bind does then is that's specific then to a server. And now this is this interfaces to the kernel. It says, I want to designate which IP address. And let me just, sorry, I'm going to cheat a little bit. I'm making sure I don't say anything that's not true. Yeah, I'm right. Sorry. I just want to make sure. Bind actually tells you, excuse me. You'll see that socket, the call to socket returns an int, but what it's returning is a file descriptor. Remember, we said that if you refer to a file, a low-level file, just by an integer ID, typically a small integer value. There's some standard ones for standard in, standard out, standard error, and then beyond that, they're just assigned incrementally. So socket will return a number that you then use to refer to this as a file. So bind, then you pass in the name of your socket file descriptor, and you provide a what these socket adder ins. And SA, I'm using the notation SA as a shortcut for socket adder, struct socket adder. And then you have to also say what the length of the address is. So in the case of IPv4, that would be 4. But you don't usually use that number directly. There's we'll talk about it, but that top-level call called getAdder_info is a relatively new API that was created and is in this edition of the book, but not in previous ones. It's become now the standard way that you get all the parameters that you're supposed to pass into all these different calls. And the idea of it then is it's a pretty small adjustment to then write code that's good for either IPv4 or IPv6. So you don't normally give the actual number from that. You get it from another place and pass it in. So binding then it's a kernel call.
I think he's totally wrong.
Designate which particular service this program is going to be hosting, or which it will be the server for, and that's given by its port number.
You can tell he's not confident because he's having to check things and make sure that he's not.
And then the next step is to listen, and that's just a call that says that will now convert the socket to a listening socket, which you need as a server. So it's a way of telling the kernel that this will be a server socket.
Bind also.
So obviously, bind and listen are related ideas, but you have to do both steps, and in that particular order to create a listening socket, or one for a server. And then the final part of that to operate is to say accept. And that means, OK, now we've established this. Now I'm actually ready to receive phone calls, is essentially what it says. This is the final step to say, OK, this one's ready to accept connection requests. And it has a similar set of arguments to socket, but slight difference. And now the interesting thing is accept will return yet another file descriptor. So the first file descriptor is the sort of generic basically accept will just hang there and wait until some client makes a connection. And when it does, then it will set up a new socket and with a new file descriptor that then the server communicates to the client via that one. And I'll talk about why it's a different file descriptor in just a second. OK, over on the client side, goes through similar steps of socket, but it doesn't have to bind or listen or accept because this is a client. And instead what it does is it makes a call to connect. So let me finish this off. So these are all on the server side. And on the client side, it will make a call to connect. And that's its job of that is from a client side is to set up a connection to a server. And so its arguments, it's a little easier to understand how connect works. So in particular, the call to socket that was made beforehand returns a file descriptor. And what this says is I want to, using that particular socket, connect to, this gives a combination of an address and a port number. And it has to give this address length, which like I said as before, it's usually that number is filled in using the return value of getAdder_info. But that's sort of the equivalent of placing the call in. And it returns just a code, which is whether the connection was successful or not. So let me just talk about these different ports and what it all means when you set up a connection. So when the server went through bind and listen, it created a listening port from that, which is the one that it's listening for connection requests on. And then the client, when it called socket, it was given a particular file descriptor for that, that socket. And it sends out a connection request that goes out over the network and lands at the server, and then the kernel hands that off to the the program that's running on that particular port and hands it off to that call will be handled by the call to accept by the server. And then, as I mentioned, accept actually returns a new file descriptor, which the server will then use as its connection point to this particular client. And the theory of that is you want to be able to, in general, as a server, be handling multiple clients at the same time. Right? If I'm communicating with Google or Amazon, you should be able to do so at the same time. So you want the possibility of, from a single host, to be able to serve multiple clients. And that's why they're all assigned different file descriptors at the server end for that particular connection. So you can think of it as the listening file descriptors, just listening for incoming requests for connections. But once it sets up a session and communicates back and forth, those are going through different ports on the server side of things, or different file descriptors, I'm sorry. Same port, different file descriptors from the software that's running on the server. OK, and then during the actual communication, then, as I mentioned, it uses reads and writes as a way to send and receive messages. And that goes on for as long as, and according to whatever particular protocol is being supported by this application. And then in the end, then, when the client is done, it closes the request. And what that looks like from the server end is it tries to read from a file, and it receives an end-file signal instead.
I think he's not.
And that tells the server, OK, this particular connection is gone. And so now it will close that particular one. And as this picture shows here, potentially the server could loop back around and accept a connection from another program. And in fact, this can be done. This is what we call a serial or an iterative. A serial server where it can only manage one connection request at a time. And when we get later in the course and we talk about multi-threading, we'll be able to set it up so this thing can start accepting requests for another connection even while it's handling one particular client. But anyways, what it will look like is the server will attempt to read it, will get an into file, it will close that particular connection, and it will go back and it will accept a new connection from a new client. OK, I'm going to jump ahead and actually start talking about some slides from that were, if you look online, they're actually from Thursday's lecture, because there's a lot of ground to cover in that lecture, and I'd like to get a little head start. So I mentioned this function called getAddrInfo, which is sort of the modern way, in C at least, to find information that deals with all the funkiness of host names, host addresses, all the conventions about ports, and some of these various structures and things like that. And the advantage of doing it this way instead of the old way is, first of all, now it sort of unifies that IPv4 and IPv6 have very similar looking interfaces, and it's fairly easy to write code that can handle either. And the other was there was problems with these old ones that they were designed in an era before multi-threading. And so they have various statically allocated buffers, which gave a lot of bad conditions that you had to watch out for in writing code, and were prone to errors of various sorts. And so this new format, it's actually harder to use in many levels because it can't hide away as many details as it used to, but it has the advantage it works better in a multi-threaded environment. The other thing that makes it hard is it's trying to be sort of the kitchen sink of protocol managers, and that makes it a little bit nasty and messy. And so we're only going to sort of focus in on the parts that we really need to make use of for this course. So in particular, there's this function called getAddrInfo, where the information you're passing is a host, which can be either it's a string, as it shows. Most of these are char stars, are actual real strings, not fake strings. It used to be, back in the old days, you used char stars as a generic pointer because there weren't void stars. But these are actual strings. So you give the name, like the domain name of a host, or you can give the dotted decimal name, but written as a sequence of characters, 1, 2, 8, dot, so forth. A service, for example, that this is IPv4 TCP service. Some other information that's associated with this particular connection they refer to as hints, because, again, this is trying to be a very generic looking call. And then you pass in a pointer, and it will fill in and return back a pointer to a data structure, which is essentially the way it's returning results back to you. And then associated with that is a call called freeAddrInfo that will then deallocate the space that's used by this data structure from the result. And then there's one called getAddrInfo string error, which lets you interpret the various error codes that get created by this routine, the value that it returns. So let's just look a little about this. And so the result that's returned by getAddrInfo is a linked list that is null terminated, just like most linked lists are, where it gives some combination of the name of this particular some naming information for the first top level one is what I showed you, the canonical name for this particular IP address. And then it gives some address information, which is an IPv4 then that will encode the IP address. And it has a next pointer to chain this linked list together. And so this is actually one interesting thing about this is it sort of takes care of that many-to-many mapping potentially of names. So if I give, for example, google.com, it will return a linked list of all however many or you saw with Twitter, it was returning about 4 different addresses. So this will return actually 5 list entries. The first will be the canonical name, and then it will give each of the 4 IP addresses that's relevant at this particular time. And then you, as a programmer, then sort of walk this list. You step down this list and typically try to use each address one after the other. And if you fail in one, then you try the next and try the next until you hit the end of the list, and then you say, oops, can't do it. And that goes whether you're writing a client or a server. So that AddrInfo, let's look back at what that is. Oh, so AddrInfo then is what gets returned is a list of AddrInfo structs. And so the AddrInfo struct contains various fields, which talks about what type of data is here, what type of socket is it, what its canonical name is, how long are its addresses. You saw that as an argument to some of the calls. A pointer to a sockaddr struct, that's the way that is encoded for IPv. What we've already seen, sockaddrs is a sort of low-level data structure that gets used, and then a next pointer to chain the linked list together. And so you'll see some of these are the arguments that then you'll use to pass into the other functions like bind and listen and connect. And then there's another version called getNameInfo, which you use when you've got an IP address and you want to find what is its domain name. And because you remember that mapping is also potentially a one-to-many. There can be multiple domain names associated with it. And so it has a similar general thing. We'll just look right now at getAddrInfo. So just as an example of how you'd write code to make use of this, and essentially just as a way of probing the DNS server, is I want to set up an argument, a call to getAddrInfo, where the string I'm going to pass the name is whatever I type in at the, to this application, to main. And it just for hints just passes a bunch of zeros. And list p, again, this will just be a pointers that I haven't actually. Oh, OK. So you'll notice hints is actually a struct itself, whereas list p and star p are just list p and p are just pointers to structs. They don't have any allocated data. So the hints, I'm just going to fill in that struct with all zeros because I don't really need to provide any hints. I am telling it that I want an IPv6 TCP connection here. And then, so what it will do is it will return back what returns an error code, but it will return to me a pointer to this linked list data structure I showed before. And now I can step through that list using standard linked list code and make calls to the getNameInfo function, which will return back domain names. And then when it's all done, I have to free up that list that got returned. Otherwise, I'll create memory stuff. So just as a demo, where am I? Oh, host info, sorry. So you can think of it, this is like a not very fancy implementation of NSLOOKUP. So the kind of stuff we already saw before, but let's, all it's returning are the different addresses. And one of the things that I found curious is it returns them in the same order all the time. Instead of with NSLOOKUP, it kept changing it. And I think that has to do with caching. No, it changed. I don't know. It's kind of interesting. You might want to play with this code. It's kind of, you can see what's going on in different places. And so you can see, though, that it's basically getting the same kind of information that you would from NSLOOKUP. It's really just querying the DNS server to do this. But that's the start of what some of this code looks like. And one of the things, by the way, when you're writing your own code, you often make use of what's called localhost. And that always just refers to the machine that you're running on, and it always has this particular IP address. So that address just refers to the machine. And as a programmer, you do all your testing on one machine. You just set up both the client and the server on the same machine and play with it. So localhost is a very useful way of doing code development. And as it shows, you can request host info for others, things given. And you can also, by the way, always give a dotted decimal address. And I'm just making it up here. And it's not very interesting because it returns back the same address. It's more interesting to run NSLOOKUP on that. So
what are you doing, bro?
That just gives you a sense. And as you've seen, this code is pretty messy stuff to work with. There's a lot of structs. You have to initialize. You don't initialize. You pass pointers. And so the code always looks a bit crufty. But that's sort of the interface as it exists. And you'll just have to get somewhat comfortable with it. So that will do us for today, then. Thanks.
Yeah, you could tell that lecture was not good.
So today's the second lecture about network programming. We got started last time. And as you probably saw last time, the APIs for this are really big and hairy and messy. And it takes just a lot of time, in my own personal experience, of rereading, looking at code, looking at examples, rereading documentation, going back and forth over that a dozen or so times before it all really sinks in. And it's one where it really helps a lot to look at example code. And there's example code in the book in that CSAPPC file that you've seen versions of in various forms. So I can lecture for days and weeks, but this really won't all settle in until you've spent time studying yourself. Anyways, I want to repeat and go back over a little bit of ground before, but last time we talked about the idea of translating from a domain name, which is something like www.cmu.edu, to an IP address, which for IP version 4 is a 32-bit address. It's usually written in dotted decimal form. And I showed you a program last time called hostinfo that you could, that we'll look actually at the code for. And I just wanted to show you today, I just did one very small tweak to that program, and I'll describe it today. And the interesting thing is it lets you look at both IPv4 and IPv6. And that's one of the interesting features of the code in the book, and it's new to the 3rd edition, is it uses a new API that lets you pretty easily write code that will work under either of these two versions of the Internet Protocol. So for example, with this slightly modified program, if I now look up the IP address for Facebook, you'll see it comes back with two different ones. And the first one is the familiar dotted decimal form, where recall that each of these digits, it's a decimal representation of a single byte. So it's a number between 0 and 255. This is a IPv6 address, which, as I told you, is 128 bits long. So that's to the 7th, take away 3, to the 5th, 32 bytes, right? And it's usually written in this hex format with : after every pair of bytes. And I think the : just means that's a 0 there. One of the cute things Facebook did was embed FACE as a hex code inside of their IPv6 address.
In an AND book, and which is zeros.
And Well, it's really different. I get very different results running this at home than I do here. And as I mentioned, you'll get different results running a DNS server depending on where in the country you are. If you repeat the same thing over and over again, you'll get different results. And that's because these very large companies are providing servers that are stationed all over the world. And as a way to sort of balance out the load of the traffic, they also have multiple server addresses that then they kind of rotate through to give you so that different people will get served by different machines. So you see, for example, Twitter or Google just gave me 2 addresses, an IPv4 and an IPv6 address. Twitter gave me 4 different IPv4 addresses. So let's look then at the code. I'll go back through some of what we talked about last time. Quite honestly, I spent a fair amount of time looking at it, so I can really understand it better, because it's not simple stuff. But as I mentioned, as we went over last time, this is sort of this giant block diagram that shows all the activity involved in setting up and running both a server and a client. And just to repeat, the idea is the server needs to fire up. You can't contact the server until that server exists. So the server is the thing that has to exist first. And all these steps are what are required for a server to begin on a machine and then to accept a connection request from the client. Similarly, once the server is set, then the client can begin. And it's like placing a call to the server. And it makes a connection request, and that's accepted by the server. And then what's called a session begins, meaning an ability for these 2 machines to talk back and forth over an internet connection. And they'll do it. This example I'll show is done by reading and writing as if they were a file. Each end looks like it's reading and writing a file. And then once the client is done with whatever it's trying to get, it will disconnect, essentially hang up its phone. And then the server will detect this by receiving an end of file when it attempts to read from the client. And then it will close that connection. But and this I didn't have stated quite properly last time. It's not going to actually shut down at that point. It's just going to return back and accept a new connection request. And this is what's known as an iterative server. It can only handle a single client at a time. Later in the course, we'll talk about how to do a multi-threaded server that can handle multiple connections at one time. So this is a pretty basic version. So the first step on either the client or the server side is this very hairy, messy, relatively new API called getAddrInfo. And the idea of getAddrInfo is it's a sort of kitchen sink, or Swiss Army knife, if you know all those expressions. It has a zillion features that sort of subsume a lot of other sort of individual protocols. So for example, it's pretty much the same whether it's IPv4 or IPv6. It lets you sort of go forward from a domain name to an IP address. It lets you go backward from an IP address back to a domain name. It supports all of those things. It will let you look up what is the port number associated with an HTTP server. So it will let you do all kinds of different things. And as a result, it's a big and messy API with a zillion features and parameters and so forth. So you recall from last time that the data structures we use to refer to a connection, whether it's an IPv4 or an IPv6 connection, is called a sock adder. And as I mentioned, this is sort of the C version of subtyping if you know a language with type inheritance. This is how it's done in C. It's done by casting. And so in particular, the sort of generic socket address, all it needs to know is a 2-byte field at the front that specifies what kind of socket is this. And then in particular, we'll be looking at what's called a sock adder in, which is an IPv4 version of a socket. And so what it needs to know is a port number, which is a 2-byte integer, and an IP address, which is a 4-byte address for IPv4. Both of those are actually stored in this structure, as I mentioned, in big Endian order, even if you're running it on a little Endian machine. And one of the interesting features of this API, this getAddrInfo, is it's largely removed the need for you as a programmer to worry about byte ordering, and that's a nice feature. So in general, for example, in getAddrInfo, if I want to pass in a port number, I'll pass it as a character string, a string representation of a decimal number, in other words. And then the code here within this API will automatically turn that into a 16-bit integer and put it in the proper byte order. And same with how it takes use of this 32-bit IP address, and you want to get it into dotted decimal form. It will do that for you without you having to worry about byte order. So it's kind of a nice thing. So getAddrInfo has a whole bunch of arguments, and some of them are essentially outputs. Some of them are inputs, things you're passing into the function, and others are really more like outputs, how it gets information back to you. So in particular, the first one is just the name of the host, and that can be either a domain name or a dotted decimal name or one of those funky-looking things with the colons that you saw for IPv6. The service is usually, if you're looking up, so if we're using this to look up, that'll actually be a null pointer. And basically what typically you'll have is one of those two will be a string and the other will be a null pointer. And the reason for that is the same function can be used either to look up a service like what is the port number associated with HTTP, or it can be what is the IP address of www.cmu.edu. The hints is something that you're passing in, and it's basically you fill in a small amount of a fairly large body of information about what specifically are you looking for in this request. Are you looking for an IPv6 information? Are you looking for IPv4? And so forth. And then what it returns back, and that's why you pass a star, is it will return back a linked list that it's generated of results. And the reason for that, as I mentioned, is that IP addresses are sort of many-to-many mapping potentially. As you saw, it's possible for a single domain name to have multiple IP addresses. It's possible for a single IP address to have multiple domain names. And so this is how they handle that sort of fact that they return a whole list of results. And associated with that, once that result gets used, once you're done with it, you're supposed to call a function called freeAddrInfo that will basically dispose of all the elements of that linked list. You don't have to do it yourself with free. And then there's another helper function called GAR_STIR_error that you use if there's an error code to help you interpret that error. And it returns an error code. So as I mentioned, it returns a linked list. That result is a linked list of these of adder structs, AddrInfo structs. And the AddrInfo struct has a zillion fields, some of which you'll use and some of which you won't. This is, for example, when you're passing in hints. Hints is sort of what you're passing in, the information, some conditions about what you're looking for in this request. And then some of these you pass in and some of it returns. And so some of these fields are ones that then you can use when you're making calls to other socket functions in the socket library. It'll fill in instead of you having to worry about what's the structure, the format of a socket adder in, and how do I convert into network order and stuff. It will do all that for you. So it's a little confusing. Stuff you're providing is stuff you're giving it, and sometimes it's stuff that it's returning back to you.
From last lecture.
And then there's an function. So get adder info is given a, it's actually give me the address information about some name. And get name info is I give you an address, and you give me back some documentation about it, including potentially a domain name. So there you pass in as the first argument is a sock adder struct. Remember for this lecture, and I think in the book, in a few places, we've sort of created a typedef to alias, so we don't have to say struct sock adder all over the place. But that's what the essay is. And it will provide back information about that address. So if you're passing in a 32-bit IP address, you can get it to return either a dotted decimal version of that or to do the DNS lookup and have it come back with a domain name for that. So this is that program that I just demoed to you, this one called host info. So all it's really going to do is use these features to, all on the command line, give a domain name, say, and it will just come back with a list of IP addresses. So, and this is pretty much the way you write code for this get adder info API. That you typically, so hints is the information I'm passing about what it is I'm looking for here. And so you start typically by zeroing out that entire field and then setting the particular things you want. So in particular, in this code that's in the slides and the one I demoed to you last time, I'm only going to be looking for IPv4 connections. And so I use the constant called AFINet, which is defined in the sockets interface. And also I'll say that I want a TCP connection, what's called a socket stream, which if you recall is the sort of protocol that 99% of the IP traffic in the world is carrying is on TCP, meaning it provides a somewhat higher level abstraction of what's going on of sending packets back and forth. So that's as much hint as I'm giving it here. And now I'm making a call to get adder info, and this argument is the name, which is I'm getting it right off of the command line here. So in my demo, it was always a domain name. I'm passing a null for the service. As I mentioned, this call you typically have one of the two is null, but not both. Hints is what I'm passing in is this is the kind of information I want. And list p will now become a pointer to the results that get returned by get adder info. So that's the call in all of its glory. OK, and now I want to go back. So I got one of those linked lists, and that will have a whole bunch of IP addresses, potentially multiple IP addresses in it. Maybe just one, maybe none, but some number of them in a linked list. And I want to walk through that list and get back the dotted decimal version of all those names, or the colonized version of those IPv6 addresses. I don't know how you refer to those, by the way. I know relatively little about IPv6, I have to confess. So then there's a function called getNameInfo, which usually you use to take a socket address, IP address, and go backward and get a domain name. But if I tell it by a flag, one of the final argument to it is a flag argument, and say what I want back from this is not a domain name, I want it in this numeric format, either dotted decimal or the colons between hex digits. So by passing that to getNameInfo, what it's going to return, and I'm passing in a buffer, meaning a char star, and some size of that buffer, and it's going to fill that in with the string representation of it. So you see, this is the way I'm going from the, if you look at this is the actual sock adder of each of the list elements. I'm giving it, it's going from that sock adder, which embedded within it, as you know, is the 4-byte IP address. And what it's doing is it's taking that, flipping the bytes, and converting it to the dotted decimal form. So this function can do a lot of different things, and I'm using it for that particular feature here. Question?
So the card is that when p is null?
If p is null, then I won't go very far. Yes, because it's a null terminated list. So, other questions? Good questions. But that's exactly the code you saw running. And all I did to generalize it to include IPv6 addresses was I commented out this line. Say I don't demand that it be AFINet is a shorthand for IPv4. So by commenting that out, it said, OK, I'll get whatever TCP connections this domain will support, and that will include IPv6 addresses. So I thought it's pretty neat. And you have to be pretty nerdy, but I am pretty nerdy to think this kind of thing is neat. But that you could write code in this way that whether you're doing different versions of the Internet Protocol, it's all one common body of code. So we've seen demo of this. OK, so now let's jump into that. Shows you sort of a little bit of this get adder info API. Now let's jump into the full-blown web server part. And as I mentioned, in chronological order, you actually want to set up the server first. But it's easiest to understand the code for the client, because as you see, it has a couple fewer calls to make. So let's go through the client. Just imagine that somewhere out there's a server that's waiting for us to connect to. So this now doesn't, perhaps, when you break it down, maybe this picture looks a little less daunting. We already saw get adder info is the way I'm going to get an IP address out of where my server is. Socket, I mentioned this yesterday or last time. It's just a local call that's used to allocate some data structures for this particular connection. And then connect is like placing a call. It's an API. It's actually sending over the internet to the server some information saying, hey, I'd like to connect to you. And then once the server, once that connection is accepted, then I can begin my session. So let's look at that. So first of all, I have to go through all this rigmarole with get adder info, but it will look pretty similar to what you've seen before. Except I'm going to give a little more information because I want this to be. I'm filling in a few more details here because I want to specify more features of this connection. So I'm saying that it's a TCP connection. That's a sock stream. I'm saying that I'm going to give it a port number in a numeric form. You could also say, as I mentioned, there's certain ports have standard names, HTTP, SSH, and so forth. And you can actually pass in the string representation of those. But I'm using this in a sort of idiosyncratic way here. And then this feature, get adder config, is a parameter that's described in the book, and they say it's a good idea to use it. And then I'm making a call to my friend get adder info, with these hints, and it's going to return back this linked list of representing the results of this request. So basically a linked list of IP addresses. So now, just like you saw before, I'm going to walk that list with except now what I'm going to try and do is for each of those say, well, here's a number, let me give that a try. And if that fails, here's another address, let me give that a try. So I'm going to just sequentially try all the different addresses. You saw, for example, 4 potential addresses for Twitter. I'll walk through all of those. And on each one, I'm going to call for a socket. And the socket is the one that, as I said, it allocates some data structures. I talked about this last time, that's why I'm rushing through this pretty fast. But you'll notice that the fields that you're filling in are actually all been generated for us by the getAddrInfo call. So whereas you used to have to remember, oh, this is a number and it should be a shortened network order and yada da, pretty much nowadays you can just say, here, I'm just going to pass you this information that this was returned by a function call. And then, as I mentioned also last time, I know I went through it pretty fast last time, socket actually returns back to you a file descriptor. And you recall a file descriptor is just a small integer, starts with 0, 1, and 2, and then it goes up from there. And so I'm going to interface with this network code as if I'm talking through files. But socket doesn't actually do anything as far as the internet goes. There's nothing going, there's not even the serious effort within the operating system. Nothing goes over the network here. So the real work here is, but it also allocates some local data structures. And then what I'll do is I'll attempt to.
See, now he's changed his story. Lecture 2, he had some more time to study up on this. And now he's saying the operating system doesn't do any serious work.
So there's nothing going, there's not even the serious effort within the operating system. Nothing goes over.
There's no serious
so the real work here is, but it also allocates some local data structures. And then what I'll do is I'll attempt to connect to the server. And again, you'll see the various arguments I have to pass to the connect command I get provided for me out of this call I made to getAddrInfo. And that's either going to work or it's not going to work. Similarly, the socket call is either going to work or not work. It'd be very unusual for a call to socket to fail. But connect, for example, will fail if the server is not available or doesn't like you for some reason. And so if that succeeds, I'm going to break out of this loop. I'm going to then free this data structure and return the file descriptor for the this particular function. Its job is to open a connection to a client and return a file descriptor for it. And this is just what happens if you fall out of the loop not having made any connections. OK, so I know I'm marching this fast. And as I said, I know from my own personal experience, I can attest that this stuff just takes time to understand because there's so many different features here. OK, but that's the idea is we're going to, now on the server side, which, as I mentioned, is actually what you do beforehand because you can't really have a client connect to a server that doesn't exist. But it's just a little bit trickier to understand what's going on. But you'll see the first 2 steps are the same. I need a socket. But then remember, what I want to do is essentially set up a server that's listening on a particular port for clients to request on it. And that's the function of the bind and the listen functions. And then the accept is when I'm saying, OK, the server's ready. I'm ready to accept requests. And it will fire that up. In particular, the accept will just stop and hang up and wait indefinitely until some connection request comes in. So if the server has no customers, if there are no clients, it will just be waiting potentially forever with the call to accept. Okay. Everything else goes through boom, boom, boom. But that one is where the actual waiting occurs for client connections. Similarly, I should mention the connect will also hang up and wait until the connection is formed. But typically, it's built in with a timeout so that it will fail if it takes too long. And you can adjust the parameters on both of these, how long you wait for, whether you wait or not. But I'm talking the typical case. So anyways, again, we'll look a little at those functions then. OK, so this, again, we have to make a call to getAddrInfo. And this time, it's not because I need any IP addresses. I already have an IP address. I'm a local server. I don't actually need to know the IP addresses of my of the clients. I usually won't know them. But I need to fill in all those nasty little data structures. And so that's what I'm going to use getAddrInfo for here. So I'm going to say this time, again, I want a TCP connection, a sock stream. I want it to be a listening for any IP address connection coming in. So it's passive, meaning it's not actively reaching out. It's passively waiting for connection requests. I'll say that I'm going to tell you a port number that I'm going to actually use as my server's port number. And then I'm going to make a call. And this time you see that I'm not giving any information about the host because I'm the host. But I'm giving the information of the port number that I'm using for this server and the other hints that I've just filled in. And then it will return a list P. Yes?
What was that?
Memset is the standard way that you set all the bytes in some number of bytes to a fixed value. It's the same as if you've used B0 before. Or B is the way you often would zero out a bunch of bytes. And if you look at the web page, and I don't know why, they say use memset, don't use B0 anymore. So alloc will also zero it out. But I'm not actually allocating anything. See, the hints is a struct here. And remember, a struct is just a bunch of bytes. And so if I make that particular call to memset, it will set every byte in that structure to 0. And this is sort of the official standard way you're supposed to do that kind of thing. That's a good question. So question.
What are AI passive and AI config?
AI passive is that it's a listening connection. It's going to be a listening connection. And AI adder config was some other argument. And quite honestly, I don't remember. But you saw I gave it before with the get host name. So I don't remember. It's a somewhat obscure parameter that's not even a required parameter. It's in the book. I'm sorry. Or you could Google it right now. One interesting thing is I didn't say that
That is a call to get adder info. I don't know why I was looking in socket there. AI adder info.
Force this to be IPv4 code. This will work for IPv4 or 6, the exact same code. OK, so again, list P comes back with a list of stuff. Typically, that list will be of length 1. In fact, I don't know why it would be anything else, but it has the same general look to it. So again, I'm going to make a call to socket to create a file descriptor that I'm going to use. This will be the one that the server listens on for connection requests. And then there's another kind of obscure thing you have to do of setting some options on that socket that will get it to free it up more quickly if there's a failure. This one I do know, and it's kind of obscure, and it's in the book, so I won't spend a lot of time talking about it. OK, but now here's the real work, is the bind call is the one that says, I want this file descriptor to be associated with this information, which in particular specifies the port number. So that's where the binding occurs for this machine. Remember, port numbers are a resource that all the different applications on a single machine are sort of sharing or are competing for. And so this is requesting, I want to use this particular port number in doing this, in setting up a server. And that may fail if the port's already in use, or if you're trying to set up a service on a port that you're not allowed to do. Like, you're not allowed to set up a service on port 80 unless you have root access. So, and then again, it passes in the information that was filled in by the call to get adder info. So we're not quite done yet. But if this succeeds, then what we've done is we've bound a port number and a file descriptor together in a socket. But all that's done is that's, again, just within the machine saying, OK, I agree. This particular process gets to be listening on a particular port. But it's not actually listening yet. And I don't know why they split this into two, but they do. And now I actually have to explicitly make a call to listen saying, oh.
So my understanding is that bind and listen are separate stages, is because you might want to bind to n number of services and ports and IP addresses or interfaces and services, however you want to view it. But you might want to bind to multiple of those. For example, like binding a single socket to listen on both localhost and on a external IP address might be something that you want to do, in which case you have to make multiple bind calls. And listen is just a call that says, hey, I'm done binding, and I want you to start accepting connections from the outside world into a buffer, and this is how big the buffer should be.
Receive connection request. And you can give as a parameter a number that says how many connection requests are you allowed to queue up before they start getting refused. And this is a performance parameter that if you set it too low, then unless you have a really fast server, people will get failures in their connection requests. But if it's too big, then you're vulnerable to certain types of denial of service attacks. So again, a little bit of an obscure feature. But the result of this is now I'm returning out of this a file descriptor that the server can use to pick up connection requests. OK, so let's do a little example of how we might actually do something. And I'm going to use as an example a rather mundane application, which is an echo server. An echo server is just one that responds back whatever it just received. And the code for it's in the book, on the slides, we're studying. So let me set up this amazing demonstration. So it's called the echo server I meaning iterative. It can only do one connection request at a time. And I'm going to set it up on my laptop here. And I'll connect to that. So you'll see that I told the server, use port 15213, which is just a random number I picked out as the port number. In general, if you want to do your own stuff, you pick port numbers that are 1,000 or greater, and they're limited to be unsigned 16-bit ints, so 64 or 65,000 something's the maximum. And as long as, and by the way, if you live in a corporate world, your ports will all be locked down, and they will not let you do this. But in the CMU environment, it has a pretty permissive policy. And actually, I'm just doing this on localhost, but you're allowed to, at CMU, open up ports like you want. So anyways, I'm going to run this client, and you'll see that the server just said, I've received a connection from the local host, not very exciting, and I've received it from port 55457. So this is the port that got assigned to the client in making the connection. The server is using port 15213. And you recall we talked about last time that a link is defined by the host and port names on either end. And that the client side is usually assigned what they call ephemeral ports, meaning it's just assigned for this particular session that I'm going to run. And now here's the amazing feature of an echo server is that you can type in stuff, and it will come back to you. because it's echoing. So what's happening is I'm sending those meaningful messages to the server. It's reading them, and it's just sending them right back again. And then the client's reading that and printing it on the screen. So it's sort of the minimum functionality you could imagine. But you can see that the server is telling you, oh, by the way, I just received so many bytes, so many bytes, so many bytes. So you can see that it's actually doing something. And then if I send it into file, which is just a control D, the client will exit, and the server will drop that connection, but it doesn't show you anything. And if I wanted to, I could start it again. And you see this time it assigned a different ephemeral port to the client. But I can only do one at a time. If I tried to now do another connection, I won't try and do it. If I tried to do it, it would just hang up. The client would hang up. It would not be able to get a connection because the server is only able to handle one client at a time. OK, so that's what the application does. And now let's see how it's implemented. It's pretty simple. The nastiness was those functions we've already seen. So here's the client side of it. It calls that function I went through called open the client file descriptor, where you gave the name of the host and the name of the port that the server is operating on. So I said here, localhost 15213. And I'm going to initialize a buffer that will be used for communication back and forth for this network communication. So now echoing means, from a client perspective, it will just read in what I've typed. So using getS or fgetS to read in what's been typed on the standard input. And as long as that's not null, meaning I don't have an end of file, then I will write it to the client file descriptor. So that's how I actually send it over the network, is I do a write to that socket that file descriptor represents. And then to get something back from the server, its response, I'll do a read. And Rio, as you call, has embedded within it what file descriptor that read is using. So I'll say read from that particular file descriptor, fill the results back into this buffer. So I'm using buff both as a sending buffer and a receiving buffer. And then just print that out onto the terminal. And this is, by the way, the new lines being included in this, not just the in all of this, and that's how it's working. So that's all that happens. So the main point you see here is that I'm using this socket like a file to both send and receive. The server code is just a shade more nasty than that to support some of those amazing features it has. So in particular, there's a weird struct called a sockadder storage that is just, again, part of this generic API that gives you a buffer of some kind that's big enough to store a name of a host, is what I'm going to use it for. And so I'm going to accept a connection. So accept, you recall, is the way it says, OK, I'm going to wait here until a client contacts this server. So that you make a call to accept, and it will just hang until that contact occurs. And then what it will return from you is a new file descriptor that we call the connection file descriptor here, which is different from the listening file descriptor. And the reason is it doesn't really show up in this code where I'm doing it iteratively. But you can imagine if I had a server and I wanted to be able to maintain 1,000 connections at once, there'll be one of those file descriptors that I pick up new requests on. And then all the other ones are the various other clients that I'm communicating with right now. And then what accept fills in here into this information, it's a sockadder struct, is about information about the client, the IP address of the client. And I'll use this call called getNameInfo, which is, again, one of these kitchen sink features that I'll pass in this client address. And it will come back the domain name of the client. And that's what you saw how it printed out when the connection was formed, where that connection was coming from. So all this business here is used to support that feature of being able to print out what's the host name and what port am I using. And this thing, by the way, client port is client host name and client port are both buffers. Yes, host name and port are both buffers, and I'm passing a pointer to those buffers, and I'm passing their length, max line. And then the call to get name info is filling those in with string representations of the host name and the port. And now it just makes a call to the echo function, which I'll show you momentarily. And then it closes that connection. And then this continues. You see the while one. This is in a loop forever, and you actually have to control C on this program to get it to quit. OK? So let me just look one more. So this now is the echo function that the server uses, and it's pretty straightforward. In fact, it looks kind of like what you just saw, except it flips around the reading and the writing. It will read some number of bytes over the connection file descriptor. And if that's a non-zero number, then it will echo that back by writing it. If it's a 0, that means it's detected an end of file, and it will just exit from that little loop. But remember, echo is within a bigger loop of accepting new connection requests. Okay, but again, just see that it reads as a way of accepting information from the client, and then it writes to send information back to the client. Good? So one interesting feature is if you want to test some programs, you can use a program called Telnet, which it used to be the old-fashioned way you used before SSH. This is how you communicated with other machines. And it's absolutely completely insecure. So don't ever use it to actually, and most places, you can't even make a connection to another machine using Telnet. It's amazing how simple life used to be. But for example, if I Telnet to myself on that port, it will begin a session, and it will in fact look a lot like an echo client because Telnet just sends information to the server, and the server is designed to echo it back, and so it will print the response. And so effectively, Telnet is behaving like an echo client for me. And I'll demo that because it's useful. I mean, this is a pretty trivial program, but there's actually times you can use Telnet. If there's a server somewhere out there and you want to give it a poke to see what's going on, as a tool, you can use Telnet. Let's see, you have to escape with the control right bracket quit. OK. So now let's move on to HTTP. I'm going to try to get rid of all the animations in this. OK, so that's sort of the basics of the low-level socket programming that you need to create client-server applications. So the best example out there of a client-server application is the World Wide Web. And you know the idea, web servers and your browser is a client. So, but all of that sits on top of, the protocols for that sit on top of the other internet protocols. So we talked about TCP, it sort of sits on top of the lowest level, the packet protocol. And then HTTP sits on top of that and uses TCP connections to send and receive data over the World Wide Web. And that's all according to a protocol that was developed starting in the early 90s, and that's what Tim Berners-Lee did initially. And it's gone through a couple revisions, but the latest one still dates back to 1999, HTTP version, 1.1. So just as some terminology, and you've sort of heard this at various points, one of the clever things about HTTP is it lets you handles different formats. You can send a JPEG image, you can send a text, and so forth. And those are all encoded in a format called MIME, which is actually just a way to take binary values and convert them into hex formatted strings. And then you've sort of heard this, HTTP version.
He is way off on this one.
So just as some terminology, and you've sort of heard this at various different ways, is one of the clever things about HTTP is it lets you handles different formats. You can send a JPEG image, you can send a text, and so forth. And those are all encoded in a format called MIME, which is actually just a way to take binary values and convert them into hex formatted strings.
MIME is not a way to do that. I believe MIME was originally used in mail clients and servers that needed to encode data. But today, if I say my MIME type is image GIF, I'm getting back raw binary data. I'm not getting hex encoded data. So the hex encoding is like orthogonal concept to actual MIME types. I don't even know why you brought that up.
And then sort of a standard for how you encode it at one end, how you decode it at the other.
No, it's not that at all.
And so you get to specify, when you're sending stuff, you specify what type of information it is. And then the other thing you've probably experienced, and now we're talking a little bit ancient history, and I'll update it momentarily. But classically, you either use static content, meaning a fixed web page that was written in HTML format and was designed to just give you information that was the same every time you looked at it, or dynamic content where you will change. So for example, a server application that's giving you the weather, it's not the same page every time, and so it will format it in dynamic content if you make a request. Nowadays, it's gotten a lot more complicated because of JavaScript and all these other sort of client-side programming languages that actually executes code on your client and communicates back and forth to get results. So I'm a little bit dated here talking about this sort of old-style way of working. But in all cases, what actually comes across the wires are some type of a file. And then you've heard the term URL, meaning Universal Resource Locator, is a combination of a couple things. One is it tells you where is that information in terms of a domain name and potentially with a port number. And then also on that particular host, where within the host is that information to be found. And there's defaults, like if you don't give anything, it defaults to index.html, for example. But URL in principle gives you where to locate something on a remote machine. And now we've seen examples of the tricks that DNS plays, so that even though you're giving a host name, a domain name, it could be any of a number of different servers, but the concept's still the same. So when I make a request then, when I'm running my browser and I want to see a web page, what it does is it sends an HTTP request out to the server to do something and to return back a web page. And there's a couple of different standard services. The most common, the one that's used 90-some% of the time is get me a page. And there's other stuff too. And then it will respond back with what's called the response line. And embedded within that response will be the thing you're asking for. But in front of it all is a header that contains other stuff that is of some range of interest of whether you really care or not. It can also come back with a response that says there's an error code, as you know, the infamous 404 error code. So let me give you a demo of this, just so we're talking a little less abstract. Computer science department's exact bytes test out when things actually work. So anyways, let's just look at what happened. So at the top is what I typed in. It's getting, in this I'm giving some the name of a particular web page that I made up just for this purpose, a fairly simple web page, and I'm telling it I want the response in the HTTP 1.1 format. And then I have to also give a host name explicitly, and the reason for this is a given machine can actually be serve multiple hosts. Like if I want to pay for hosting of some domain name, say to GoDaddy.com, right? It's serving hundreds or thousands of different domain names, and so it actually uses that host information to figure out, oh, which particular web customer am I supporting here? Okay, and now it came back with its response. And it said the code 200 means that was accepted, which tells you OK. And now it comes back with this is the header information. It says here's the date, here's the server, here's some cookie information. The overall content is exactly 479 bytes, and it's a text HTML format. And then it will return back the raw HTML that this web page had, which is what I actually, I typed that. I did this by hand, but you can imagine other types of things. And then it just codes the connection. So you can see that this returned both the header information and the actual content information as well. And so that's a general idea of what an HTTP is. And the slide text has a really interesting code that I recommend and study called Tiny, which is the world's smallest functioning web server. And what it's really only a couple pages of code. It does some very basic handling of static and dynamic content. It's something you can sit down and read and study, 239 lines of code. Now, it lacks a lot of features. It does a very bad job of handling errors. It doesn't have a lot of the functionality you'd come to expect in a server. So it's been stripped down to the sort of barest bones to demonstrate the concepts. But it's pretty cool that it works. And I can say this because I didn't write it. So the overall idea then is it's a server. So it's receiving requests from clients, from browsers, saying, I want this web page, or I want to execute this particular dynamic program to get dynamic content. So it comes in with a request, a GET request, like you just saw, and it splits that. It picks out what's called the URI, the argument to the GET request. A URI is a universal resource indicator, which is not a complete, potentially URIs are a superset of URLs. URL has to include the host name and all the information to get from anywhere to anywhere. But a URI can just be a portion of that information. And then it will determine, is this a request for static or dynamic content? I'll show you both of them, hopefully. And if it's a static content, all it has to do is retrieve a file on its own machine, send that back in that format that I just showed you. So let's take a look. So this is sort of the guts of the static server. So what it's done is it's received a request. This is a helper function of this code, so I'm kind of buried down in the middle. But what it's picked out is the server has received a request for a particular file name from the URI. And it's also done a lookup through an OS call to figure out how big is that file, how many bytes long is that file. And it's also given the file descriptor that is the file descriptor for this particular connection. So all it's doing here, you'll notice, is it's doing a bunch of sprintfs into a buffer. And what it's doing there is it's formatting the header information as a byte, as just a big long string, including the returns in it. And one of the features, which don't ask me why the great wisdom of Tim Berners-Lee did, or whoever figured this out, but every line has to finish with both a carriage return and a new line instead of the usual Linux thing of just new lines. So that's what the \r\n means. Well, you'll see it's going to respond back with an OK and some of this kind of information that's not very exciting. But the ones that really matter are the length in bytes that has to be given and the type. Where's he getting the file type? Oh, there's another function. Oh, I remember why. There's another helper function here that, because this supports not just text, but also GIF and JPEG.
This is like massively inefficient. He's creating all these strings over and over again. I would not do it this way. If you're gonna create a buffer, like he's reading from the buffer, writing the same data back into the buffer. If you're gonna do that, just like keep an indice into the buffer and just write into it. Like, don't like read everything back, do the format string stuff, and then write it back multiple times. It doesn't make sense.
Another function somewhere else that's telling which MIME type is this particular file. And so it's putting that together, and it's and now it writes that out. So it writes the header information out to the client. So it's sending back to the client. And then it's going through a few gyrations here to get the file, open it up, and then there's a function called mmap. Have you guys covered mmap yet? Yeah? Which is just a tricky way to avoid having to actually read the file into the machine, but basically be able to pass off a pointer directly to, or into the, read it through explicit read commands into yet another buffer. It just avoids one step of buffering. So all it does is map then from the operating system where this particular file is located, and then writes that. So now it's sending it off to the client. And so this could be done with a regular read, but this is a little bit more elegant way to handle it. And you'll notice, by the way, that the content length here is the length of the file, and does not include the number of bytes in the header. So the header comes first. There's no length associated with it that's sent back. But now the only way that the client knows exactly how many bytes that response is going to be is by picking out this number in the header and reading that many bytes from it. We'll see that in a minute. But anyways, this is the way a file gets sent. So now let's just real quickly look at dynamic content. So the idea of dynamic content is it lets you pass in parameters to a program that then gets executed. And the purpose of that, what that program then has to do is compose a web page and send that web page back to you. So I'm going to demo this with a feature built into here. So in particular, you probably can't, you can barely see, I don't have a good way to blow up the thing. But you can also see what kind of things I look at. But anyways, if I just say localhost colon 15213, that means port number 15213 on my local machine, which is currently running the tiny web server. And the only web page available for it is this rather stunning figure here. But it shows that it can handle both GIF content and text, HTML. But it also supports another interesting feature, which is a program that can add two numbers called add.com. It's our idea for a startup company that didn't quite make it. So in particular, it's our idea for So in particular, the idea of this is it's a CGI program. It's a dynamic content. So that I'm passing two numbers embedded within the URL of my request. And it comes back with a web page that is beautifully formatted like this one. So you can't see very well, maybe, but if you look up there, the teeny tiny print at the top, you'll see localhost colon 15213, that's the web server, then /CGI-bin, that's what this particular server and what most servers do for interpreting dynamic content. And then a program, it's an executable file called adder.
So, like,
and then the argument string that you embed in this kind of curious way, the question mark,
the
and then use ampersands to separate out the different fields.
Structure.
So that's all pretty standard way of handling dynamic content. And as I said, nowadays there's a lot fancier ways of doing it, but that's sort of the basic way. And you'll see it's still being used today.
2016.
So imagine that this time it's a GET request, but instead of the adder function, it's some other Perl program that is sitting on the server somewhere called env. And we won't worry about what that program does. We'll just show you the idea behind it. So in particular, there's a GET request comes in, and it says CGI bin, and then the next argument is interpreted as the name of a file. And what will happen then is that the server will spawn off a process using our friends fork and exec, which you know so well now from doing the shell lab. So and that program will execute. And its job then is to generate a file in HTML format, and then the server will send the result back to the client. So there's a few details we've got to figure out to make this work. One is how will I actually pass arguments? How will env.pl know what's being passed to it as arguments? How will env.pl get whatever page HTML it creates back to the server so that the server can send it to the client? Those are all the sort of details of the CGI specification. CGI stands for Common Gateway Interface. So you just saw a demo of ed.com. And so let's just look at how this works.
It's such a waste of my time.
So as I mentioned, the way things get passed is within the URL, you include the program name, and then the question mark is what is like the terminator for the program name, and then all the other arguments with ampersands between them. And you can't have any blanks in here, so they put %20s, and as you've probably seen, various other, those are called escape codes. When you can't use a particular character, how do you encode it in some other way? So the first thing is, how does the server then pass the argument to the program that gets executed? Well, it's really weird. The way it does it is by creating an environment variable for your machine that's called query string. And so the server defines that environment variable. And then the job on the CGI side of the script is to then retrieve that environment variable as a way of getting the string. You can already see, hey, wait a minute, what if you were running multiple servers at once? You can see you've got a problem here. But actually, no, environments are specific to particular processes, so this will work. So it's creating for the application program that we'll be able to sort of retrieve from the operating system, essentially, what arguments were passed to the, are being passed to it. And so this is what the code looks like for the dynamic server. Again, it's going to write back some information back to the client. And let's look at this. And now it's going to set up this CGI query string environment variable, and then use our friends dupe and exec basically to redirect the standard output to its client. Let me look at this. Oh, I'm sorry. File descriptor is the client's file descriptor. So it will tell, it's going to, oh, and we're in a fork, I'm sorry. So now we're in the child process. OK, let me read all the code. And within the child process, it's going to rename its standard output so that it's writing directly to the client, and then call exec, which, as you know, is the way you take this program, which is just given by a file name, and fire it up and get it going with that defined environment value. And then this is the parent. We'll just wait until the child completes. OK, so now we're almost done. So now this is what the actual program, the adder program does, the one that the CGI program, the one that's been forked off and exec. So it creates then the HTML that you want to send back. And here it's pretty mundane. The only actual HTML in here are the P's, meaning paragraph markers. So this is literally generating HTTP, HTML content, and storing them all in as a string called content. In the top levels and out. And so again, let's just do a net. What they can much and what burners handle different content type. Set up these dynamic things by forking off a process every time, which is an extraordinarily inefficient way to do it. Like to kind of, get different agents to talk to each other over the internet. People were working on much more exotic wide web, and it's gotten a lot more complicated generated. So it's actually what people say about this early World Wide Web, and it's gotten a lot more complicated, is the best thing Tim Berners-Lee was to figure out how simple it could be. Because other people were working on much more exotic ways to get different agents to talk to each other over the internet. And what Berners-Lee figured out is we can just kind of cobble together standard ideas of sockets interface, have some protocol, pretty straightforward protocol, handle different content type, set up these dynamic things by forking off a process every time, which is an extraordinarily inefficient way to do it. Like to add two numbers by forking off a whole process and doing it is totally absurd, but then so is ed.com. But you know, it's not, in some ways, he took a bunch of ideas that existed and figured out how to put it together, and all recognized the value obtained from that. And it took the internet from being something that was certainly used by nerdy people to talk to each other and opened it up to all the things that we know of today. So it was a huge step forward, and I give him full credit, even if from a technical point of view, it's actually fairly straightforward. OK, so that will do us for today.
These lectures were a complete waste of my time, but we did them.
Well, good afternoon, everybody. Welcome. Good to see you. So this week we're going to study how to incorporate concurrency into programs. Now, we've seen concurrency before in the form of processes, exception handlers, and in the case of processes, it was we used processes as a mechanism to run multiple independent application programs. Okay. Now, but concurrency also exists in application programs. Now, we've seen a little bit of this when we study signal handlers. Okay, so a signal handler is a concurrent flow that runs concurrently with your main application program. Okay, and we've seen how some of the difficulties that can arise when we introduce concurrency in our programs. So even with something like a signal handler, which isn't doing very much, it's very hard for us to reason about this kind of thing. We have two different flows running at the same time. Like our brains just tend to be kind of sequential. We want to think about things happening one after the other. And it's much easier for us to reason about that. Reasoning about multiple things happening at the same time really causes problems. And that the fundamental reason is that to really reason about, say, two concurrent flows, we have to account for all of the possible interleavings of those flows. Okay, and that grows exponentially with the number of flows. Okay, so you saw this with your signal handlers when you did Shell Lab. You had two concurrent flows, the main program and your signal handler, both accessing a shared resource in the form of the jobs list. Right? And you had to be very careful to prevent an interleaving where that data structure was being referenced in an inconsistent state. Okay. So what we're going to do this week and into next week is we're going to look at that kind of application level concurrency, but in a more principled way than we encountered with signal handlers. So as soon as you have multiple flows accessing shared resources, all kinds of bad things can happen in your program. And these have been these bad things, these problems that occur have been objects of study in computer science for decades. But the kinds of things that can happen are races, which we've seen when we did the Shell Lab, where the outcome, whether a good or bad outcome, depends on some arbitrary scheduling decision. Right? In the case of one of the races we saw in the case of Shell was the case where a child, just because of a scheduling decision by the kernel, runs and finishes before the parent has a chance to add that child to the job list. Okay, so that's a classic example of a race. And similarly, if you have two people that are accessing a reservation system for an airline, who gets if they both access at the same time, who actually gets a seat just depends on various scheduling decisions that are going on in the reservation system. Another kind of a problem that occurs is deadlock. So deadlock is a condition that exists where you have multiple flows waiting for an event that will never occur. Okay, so using printf in a signal handler is an example of this kind of problem, or introduces the potential for that kind of problem. Okay, so in your main routine, you execute a printf, and that printf acquires a lock on some system resource. I think it's a terminal lock. Okay. And then after that main printf acquires that lock, it gets interrupted by a signal handler. And now the signal handler, if it does a printf, that printf will try to acquire that lock, but it won't be able to get it because the printf in the main routine has it. So now your signal handler, the printf in the signal handler, is waiting for an event that will never occur. It's waiting for that lock to be released. And it will never occur because the printf in the main routine can't release the lock until the signal handler returns. And the signal handler can't acquire the lock until the printf in the main routine terminates. So that's a classic example of deadlock. Another more from real life. Imagine that all drivers follow the rules very precisely. And the rule for a four-way stop is that whoever gets there first gets to go first. Okay. So if four cars arrive at the intersection exactly the same time, then you have a deadlock. You have none of the drivers was first, so none of the drivers goes. And so they're all waiting for a condition that'll never occur. And then other classical things that can go wrong are things like liveness, starvation, fairness. So this starvation occurs when you're trying to do something, but you fail to make progress because somebody else keeps getting all the work. Right? So if you had two processes and the kernel always scheduled process A instead of process B, that would be an example of process B being starved out because of an improper scheduling decision. And then we would say that scheduling policy to always schedule B is unfair. Right? So it doesn't have this property of fairness where every entity in the system gets sort of a reasonable chunk of the processor. So, like I said, this concurrency has been studied for years. It's a very deep, difficult topic because of this sort of exponential explosion in the number of interleavings. So we're not going to cover all of them, but we will cover some, so you get a reasonable idea of how to incorporate concurrency in your programs. Now, for our study of application level concurrency, we're going to use servers as a motivating example, and the reason is that you cannot write a correct server without using concurrency. Okay. So it's a really good motivation. And here's the reason. So far we've looked at servers that are iterative. Okay, so they only process requests from one client at a time. And once they finish processing a request from a client, then they go on to the next client. Right? So like with our iterative echo server, you can see each of these clients makes a connection request. Then it writes a line of text to the server, and then it waits for the server to echo that back. And in this case, this simple case, it just closes. Okay, and the server waits for a connection request and accept, and then waits for and then once it accepts that connection request, it reads and waits for that client to write something to the connection, and then it echoes it back, and then it waits for the next line until the client closes the connection, and then the server closes its connection, and then only then does it do another accept to wait for the next connection request. Okay, so in this example, client 2 is also making a connection request, but it never runs. It has to wait until the server actually echoes back the response. Now there's a little subtlety here that in where exactly this client waits. So the semantics of connect, you would think that connect would block until the connection was established, but actually if you try this out, it turns out that connect
actually initiates the connection process inside the kernel, but then it returns before the connection has been established. And then it does a write, and that write also returns immediately. Right? So it doesn't wait until the server reads that the string that was written, and it doesn't block until it calls the read function, waiting for the echoed response from the server. And so it doesn't block until it hits this read, and then it spends it waits, and finally the server accepts the connection request and then writes the string, echoes the string back to the client. So the call to connect actually returns immediately, and it exploits this feature in the kernel that can queue up these connection requests. Okay, so the kernel now is going through all the process of setting up the connection, but the application program continues. And then the write inside the client doesn't block because the kernel can also queue up the data that's written. So it'll queue it up, remember that it was written. When the connection actually gets created, then it'll send that data along. But there's no way to avoid the read from blocking. Right? A read can't return until it gets some data. Okay, so read has to block. Okay, now here's the fundamental flaw of an iterative server, and the reason why we have to write them with concurrency. Okay, so let's say in our echo server example, we have a client that creates a connection, requests a connection, it's accepted in the server, does the write, the server echoes back one string, and then the client blocks again, or instead of doing the next write or closing the connection, the user goes out to lunch and never types in a string to the echo client. Okay, so at this point, the server calls read, and then it blocks, waiting for this user to type in something so that the client can send it to the server to be echoed. But the user's gone, gets hit by a truck, who knows. Anyway, so this read then blocks for an indeterminate amount of time. Right? And while it's blocking, client 2, which also wants service, it has to block. Okay, so now you're in an untenable situation where one client has sort of totally affected all of the other clients in the system, and none of the other clients can get service. So if this were a web server, if one client for some reason blocked, no other users would be able to use that web service or look at pages on that site. So obviously we can't have this. Okay, so the solution is to write a concurrent server instead of an iterative server, where we'll have a separate concurrent flow handle each client's request and interact with each client. So now if one client for some reason is slow or misbehaves or blocks the system, other clients won't be affected because those clients will be handled by concurrent flows. So there's several ways, a number of ways to create these. Yes?
For an iterative server, could it queue up reads from multiple clients, from like say 4 or 5, if there are other clients contacted and send their writes over and queue up all those?
It actually could, and in fact, that's a form of concurrency. Okay. So the question is, could the server queue up requests from clients? It could, but I guess actually it would have to queue up. It would somehow have to accept those connections, right? So that wouldn't work. So somehow you'd have, since the accept calls are iterative, sequential, there's no way to get data from those other clients. Okay. But actually, what you're suggesting is very similar to something called an event-based server that will, which is one of the ways we can create concurrent flows. So there's 3 ways to create these concurrent flows. One is to use processes, okay, like we've already seen. Okay. So the kernel, so in this case, the kernel handles all the scheduling for us and interleaves the process execution automatically for us. And then, as we saw before, each flow has its own private address space, so that each flow is independent and scheduled by the kernel. Okay. Now there's another approach called event-based, where the programmer manually interleaves the flows. Okay, so instead of relying on the kernel to interleave these different flows, the programmer creates these flows and then manually interleaves them. Okay. And since it's one program, all of the flows share the same address space, right? So they have access to all the same global data structures. And they do this interleaving using a technique called I/O multiplexing. And I'll talk briefly about that, but it's addressed in much more detail in your book. The third approach, which is kind of a hybrid of process-based and event-based, is thread-based. So each of these flows is implemented using something called a thread. The kernel, like processes, the kernel automatically interleaves these different threads. But unlike a process, each thread shares the same address space. Okay, so each thread has access to all the global variables declared in the program. So it's like process-based in that the kernel automatically schedules it for us, but it's like event-based in the sense that every flow shares the same address space. Okay, so let's look at all 3 of these approaches in more detail. So the first approach is to create these flows using processes. So in this case, this is our echo server example. The client requests a connection and then calls fgetS to wait for the user to type something in at the keyboard. But the user's gone, and so fgetS, this client just blocks in the call to fgetS. So the server, when it gets it accepts the connection request and returns from the accept call. And after it returns from the accept call, it forks a child, and then that child process now will be responsible for interacting with client number 1. So the child blocks waiting for data from client 1, which is never going to show up because the user left. Okay, but that's okay because it doesn't stop the server. The server, after it forks a child, goes right back and calls accept. And now accept can accept the connection request from client 2 and fork off a different child that can interact with client 2. So that child will read. We'll see that this must adversely affect other clients. Okay, so now let's do this in order to have a sort of a working server implementation. All right, so how would we actually program this process-based concurrent server? It's actually surprisingly compact. Right? So we're going to pass in we've got in a prototype of use the SN as the argument to this program. And then it calls returns with the address length of that address. So in the case of IPv4, it'd be 4 bytes. And then the accept returns this connected file descriptor that the child that it can use to read and write and interact with the client. So it forks the child, and then the child closes its listening descriptor, and then it calls the echo routine to interact with the client. And when the echo routine returns, the client closes its connected descriptor and then exits. And so this close isn't absolutely necessary, but we just did it to be careful. Okay, now the parent, and this is important, closes the connected descriptor because it's not going to use that connected descriptor. Only the child will use that connected descriptor. So in order to avoid this memory leak, it's very important for the child to close this descriptor. Okay, because remember, the server's running in an infinite loop. I mean, in theory, it would never terminate. Okay, and then to avoid a memory leak, we have to, in our handler, we have to have a sigchild handler that will reap all of the children that have terminated. Okay, so let's look at a little more detail how this accept works. So you have a client with a client file descriptor, and then you have a server that creates a listening descriptor. So let's say that's descriptors are indexed by small integers. So let's say that index is 3. The descriptor number is 3. So the server blocks an accept, waiting for its connection request. The client makes a connection request using the connect call. Okay. The server accepts the connect call, and then it creates a child. And then the child interacts with the client using the connected file descriptor that was returned from the accept. So that would be, say, descriptor number 4. It'd be some different number. Okay, so the execution model we have for these process-based servers is that we have the server processor listening for connection requests, one after the other from clients. And then we have multiple clients interacting concurrently with multiple children interacting concurrently with multiple clients. Okay, since each of these children are processes, there's no shared state between them, and both parent and child inherit the inherit the descriptor table, so they both have copies of listenFD and the listening descriptor and the connected descriptor. Okay, and as we saw before, the parent must close its copy of the connected file descriptor. The child should close the listening descriptor, but it's just because it's not needed. All right, so these are actually pretty simple to create. There's just a couple of things you have to keep in mind when you build a process-based server. So firstly, as with any process that creates children, it has to reap these children that have terminated to avoid this memory leak. The parent process has to close its copy of the connected file descriptor. And there's a couple reasons. In fact, if it doesn't, it'll not only create a memory leak, but that the state associated with that descriptor will actually stay around forever because the kernel won't close that connection. So as we saw when we looked at file I/O, this is the same kind of file I/O we looked at before. So the kernel keeps a reference count for each socket that's open. So after the fork, now there's a parent and a child which are accessing the file table associated with the connected file descriptor. Okay, and the connection won't be closed until the reference count for that connected file descriptor is 0. Right, so that file table entry won't be removed from the kernel until there's 0 references to it. Okay, so both the parent and the child have to close that descriptor. The good thing about process-based servers is that they do the job for us that we asked them to do. Right, we wanted them to to interact with multiple clients concurrently or have that ability. There's a very clean sharing model. Right, so there's private address spaces between all of the children and the parent. They share. They have separate descriptors, but they have separate copies of the descriptor table, but they share the same open file table. Okay, and there's so in some sense this is the simplest possible way to create concurrent servers. And if you can get by with not sharing any global variables or sharing address spaces, then this is the way to go. Now, the disadvantage is that there's additional overhead for processes. Right? Even with this copy on write trick that we saw for sharing the address space between the parent and the child, it's still non-trivial overhead. And you have to actually do a lot of work if you want to share data between processes. So let's say you want to have some kind of a shared cache between multiple processes. You either have to use files, okay, on disk, or if you want to share memory, you have to use some kind of memory mapping, or you have to use these interprocess communication mechanisms, which we haven't talked about, but there's ways. Pipes are probably the ones you're most familiar with. So a pipe allows one process to send data to another process, and there's ways to share memory between processes, but they're cumbersome and have to be implemented with care. Okay, now the second approach is we call an event-based server. So the idea here is that the server maintains a set of active connections. So it has an array of connected file descriptors from different clients. Okay? And then it determines which of those, and it also has a listening descriptor. And then it determines which of those descriptors have pending input. And it determines this using a system call called select or epoll. There's several ways to determine this. But basically using select or epoll, you can determine which of a set of descriptors has pending input. Right? And so the arrival of input at a descriptor is called an event because it changes the state of a descriptor. Okay? So an event in general is always some kind of state change. Okay? So in this case, when data arrives on a socket, that's a change in the state. So there was no data before the event. After the event, now there's data that the server can read. Okay? So if the listening descriptor has input, then the server calls accept to accept the connection. And then all connected descriptors that have pending inputs, it services those. It reads from those in some order. Okay? Now the details for how to do this are described in the book. But basically, conceptually it's pretty simple. It's actually tricky to implement. But the idea is that there's some set of active descriptors. Right? There's some set of descriptors, connected descriptors that you're using, that are being used right now to interact with the client. There's some that are inactive, so if descriptor was closed, then it's no longer active. Right? And then there's other descriptors that have never been used. So we just have this array of descriptors, and then we record their, the descriptor number for each of those connected, for each of those descriptors. And then using select or epoll or some other mechanism, we somehow determine which of those active descriptors have input, and then we service each of those. In the case of listenFD, by calling accept. In the case of these connected descriptors, actually this should be conFD, not clientFD. In the case of these connected descriptors, we read the data from them. And when we read the data from each descriptor, we do some work. Okay. So data arrives at a descriptor, and then we read that data, and then we do some kind of work. Okay. Maybe in the case of an echo server, we echo it right back. Okay. In the case of a web server, we may, if that data was HTTP request, we might go and fetch a file from disk and return it. Okay. But in any case, we notice that the descriptor has some data, we read that data, and then we respond to it in some way. Okay. So that response, those multiple responses, are concurrent flows. Okay. When we're interacting with that client, we're creating concurrent flows, a concurrent flow for each client, and we're servicing those clients concurrently. Okay, so even though it's a sequential program, right, we're not using fork or anything, it's just a C program, straightforward C program, we're writing it in such a way that we're creating our own concurrent flows. Okay. So there's, as with any approach, there's advantages and disadvantages. So a big advantage of event-based servers is that it's one process with one address space. Right? So it's very easy. You can use conventional debugger, GDB, to step through. You can see everything. You have access to everything. So in that sense, they're much simpler to debug, understand. And then there's no process or thread control overhead. So when we service a particular descriptor, there's very little overhead. Right? The only overhead is sort of determining that descriptor has input available. Okay. And so because of that, this is the high-performance web servers like Node.js, Nginx, Tornado. They all use this event-based approach. Okay. If you want to get over 10,000 requests per second, you have to go with something like this. Okay. The disadvantage is it's much harder more complex to code up than the other processor thread-based designs. And it's very difficult. So one of the hardest aspects of writing an event-based server is that you have to figure out how much work you're going to do in response to an event. Okay, so let's say this server is a web server, and you get input on one of your connected file descriptor. The simplest thing to do would be to then assume to read the entire HTTP request and not return until you've read the entire request. Okay, so in that case, the amount of work that you do in response to an event is very coarse-grained. There's a lot of instructions because we're going to read every single line in that HTTP request header. So that's an example of coarse-grained. It's very simple because every time you get a request on a connected descriptor, you just read the whole HTTP request and then send a response. Okay, so there's on the other hand, it's vulnerable because what if a client misbehaves and doesn't send the entire HTTP request? What if it sends half of the request? So if you were going to design an event-based web server, you probably wouldn't want to do that, right? Because a single client, we'd be back in the situation we were before, where a single misbehaving client could sort of shut down the whole server. So you might say, well, my unit of work that I do in response to a request will be to read a single line from a request. Okay, so I'll read a single line and then I'll return. Okay, so now we're interleaving reading single lines. And once I've read the entire request, then I'll send the response. So that's better, right? So a misbehaving client, if it's sending like whole text lines at a time, even if it stops halfway through, we'll still be able to make progress and service other clients. So that's a finer grained approach. It's better. It's probably more robust than waiting for the whole request, but it's still vulnerable because the client could just send a partial line. So now we're back. So really, the only way to write a robust event-based web server is to be able to handle partial lines. Just read when there's data available on a descriptor. You just read whatever data is available. You remember how much you read. If it's not a whole line, you somehow have to remember that. You have to buffer it, remember it. So now it's getting really complicated, right? But that's the price you pay for this low overhead, sort of easier to debug kind of model. And then another disadvantage is that you can't, since it's really a sequential program, right? It's one C program. You can't take advantage of multiple cores. So the only way to get sort of more performance out of something, an event-based server, is just to replicate copies of that server. Okay? But you can't make an individual server go faster by using multiple cores. Okay, the third approach is to use threads to create these concurrent flows. It's very similar to processes, but there's some important differences. So let's look first at what we mean by a thread. So let's go back and look at the traditional view of a process. So we think of a process as some context, that's data structures in the kernel, okay, data that the kernel keeps about that process, as well as this private address space, which contains a stack, code and data, and then the stack. Okay, and then as part of the process context consists of context that's associated with the program, like the registers, condition codes, program counter, stack pointer. Okay, and then it contains kernel context, which is information in the kernel that the kernel needs to implement this idea of a process. Okay, so all of this data is actually stored in the kernel, but some of the data is directly associated with the program, and other data is sort of support data that the kernel needs to implement processes. Okay, so let's just take this picture, and we're just going to move things around a little bit. So what I've done is I've taken the stack off of this virtual address space and sort of pulled it out along with its stack pointer and the context that's associated with the program. So the data registers, the condition codes, the stack pointer, and the program counter. Okay, and I've just renamed it thread context instead of program context, but it's the same thing. And I'm going to call this whole thing, the combination of a stack and this thread context, I'm going to call that a thread. And then everything else remains the same. We still have our code and data, and we have the kernel context. Okay, now by doing this sort of refactoring and just moving things around, I can now imagine, so this stack isn't very much, right? So there's this stack space, and then there's a little bit of data here in the form of some registers and some things to be stored, but this is a fairly small amount of data. Now, when I refactor like this, now I can think about there being multiple threads associated with the same process. If I just keep different set of data, thread context for each thread, and then a separate portion of the stack that's associated with that thread. So now each thread shares the same code and data, the same virtual address space, has the same kernel context, okay, the same I/O structures. But now it has its own separate individual stack. Okay, so local variables, things that you would store on a stack now would be private, sort of independent, and it has its own program counter, its own stack pointer, its own set of registers and condition codes. And then the one difference now is that each thread, instead of there's still a process ID for this process that's part of the kernel context, but each thread now has its own thread ID as part of its thread context. Okay, so now the kernel can just treat each of these as separate flows, right? So it's just like a process now. The kernel can remember where each thread has its own program counter, but they're running code out of the same code section in the virtual address space. So they're sharing code, sharing data, but they have their own program counter, so the kernel can create each of these threads as a separate flow of control that it then schedules just like it does a process, or a similar way it does as a process. But the difference is, the reason that 4 threads in the first place is that when the kernel wants to context switch from one thread to another, there's not that much information that has to be saved and restored. It's just a small amount of data. So the kernel has to save the data thread 1 context in some data structure some way, and then restore the context for thread 2. But we're talking about a very low overhead kind of operation. Right? It doesn't have to mess around with page tables, virtual address space, or any other process context. So threads are kind of like processes, but they're different in the sense that they share the same virtual address space. And unlike processes, which are created by fork, which creates a strict process hierarchy, threads are just pools. You can think of threads as pools of concurrent flows that access the same code and data. And then the kernel is responsible for scheduling those flows in a way that so each flow gets time on the processor. So much like processes, much like concurrent processes, we say that 2 threads are concurrent if their flows overlap in time, otherwise they're sequential. So this is the exact same example that I showed you when we looked at processes. So here instead of 3 processes, we have 3 threads running it within the same process. Thread A runs for a little bit, and then the kernel decides to swap it out and run thread B. So then thread B runs for a little bit, and then the kernel decides to give thread C some time, so it saves thread B's context, restores thread C's context, and sets the PC to the PC value in thread C's context, and so C runs, and then the kernel decides to give A some time again, so then A runs some more. Right? So because thread A and B overlap in time, they're running concurrently. B and C don't overlap in time, so they're not running concurrently. But A and C are concurrent because they overlap in time. And so you also have the option, if there's multiple cores, then a thread can run on each core, so then you can have true parallelism. Okay, so like I said, threads and processes are similar ideas, but in the sense that each thread and process corresponds to some kind of logical flow, and they can run concurrently with other flows, and each is scheduled and context switched by the kernel. But they're different because threads share all code and data except their local stacks. Okay? And in fact, those local stacks, although each thread has its own, it's really just sharing the same stack. And so it's really the same portion of the virtual address space. It's just that each thread is assigned its own part of that stack. Okay? So even though threads have their own individual stacks, since it's all part of the same virtual address space, a thread can access the stack of any other thread. And that's not a good thing to do, but it's possible. Okay? So processes don't share any of the state. Right? They have their own private address spaces. And threads are less expensive than processes. It's cheaper to create them, and the main reason is that there's just less context associated with the thread than there is as a process. And so in our system, when we measure we just create and wait for create a process, wait for a process over and over again, and then measure the time. It turns out to be about 20,000 cycles to create and reap a process, about 10,000 cycles to create and reap a thread. So the kernel provides threads to us using an interface called pthreads, POSIX threads. So this is a fairly recent standard that all Linux, Unix systems, and Windows, Macintosh, so this is a sort of standard POSIX standard for manipulating threads. And so you can do things like create and reap threads. So this is sort of like fork, and this is sort of like wait, but not quite, because it doesn't create. There's no hierarchy associated with these. You can just like getpid. There's a function to get your thread ID. You can kill threads, so one thread can kill another thread. There's a function to exit a thread. The normal exit system call terminates all the threads, and return is similar to pthread exit in the sense that it just terminates the current thread, the thread that calls it. And then there's ways to synchronize access to shared variables, which we'll look at on Thursday in more detail. Okay, so here's the pthreads hello world program. Just terminates the current thread.
Well, I think I might take a break here. Yeah, I'm getting in my breakfast time here, so let's modify this to be 9:15, and and I will take a break for breakfast. And then this can be pulled down to like 1. Pull this down to be 9:15 or 10:15. 2, 1. This will go to 9:15. Oops. And then afternoon stream, 2:15, 2:05. Okay. Cool. All right, I'll take a break here then, and I'll be back on at 10:15 to resume these lectures. Again, these lectures, I'm just going to knock them out one after the other because most of this is just a review for me, and I just want to complete all the lectures. So, yeah, that's going to be the remainder of today, is just doing all the lectures. Cool. All right, I'll be back on at 10:15. Oh, God. I clicked on the wrong thing.